So this is a joint work with two computer scientists, David Gu and Jin Song. And Wu is a graduate student in Crown. He was a student of Song, and he's now in Crown. So I'd like to tell you something about, it's a sort of mix of mathematics and computer science, but of course I'm going to tell you the mathematical part of the story. But I'd like to show you some of the softwares produced by Gu as well. So let's begin with the simply connected surface S. So here is a 3D scanned human face. It's a simply connected. And we really think of this as a Riemannian metric. It's the metric induced from the Euclidean three-dimensional space. So the uniformization theorem of Poincare and Kerb says that if we give any Riemannian metric, it may not be even complete, on a connected surface, then we can make a conformal change. I can produce a smooth function, lambda positive function on the surface, and I change the Riemannian metric by multiplication. So this is going to scale the metric pointwise in tangent space, and that's not going to change the notion of angles. After you make the conformal change, then the metric is a complete Riemannian metric of curvature -1, 0, or +1. Okay, so that's one form of the uniformization theorem. In fact, there is a uniqueness part as well, but let me just ignore it for now. So according to the uniformization theorem, this human face, because this has a boundary, is going to be is going to have a complete hyperbolic metric of curvature -1, and therefore it's a round disk. And so there is a conformal map from the human face to the disk, and we really want to compute it. And so here is a result of our software. And this, so I'm going to justify for you that this picture is real. So the process is really convergent. So there is a canonical map sending this dot to here, and this map is angle preserving diffeomorphism. So the motivation is are there any discrete versions of the uniformization theorem for polyhedral surfaces, and does it converge to the smooth case? And so I will tell you the answer here is true for compact closed surfaces. This is like uniformization theorem was first proved by Poincare and Klein for closed surfaces, and then it was much later that Poincare and Kerb proved for non-compact simply connected surface. And so we have a result for compact surface, but I have some questions for the non-compact simply connected polyhedral surfaces, and so I'd like to tell you by the end of the talk. So let me just begin with some basic definition of polyhedral surfaces. So I take this surface S is a connected surface, and V is a set of discrete set of points. And so for now, let's take S to be compact. V is a finite set of points. A polyhedral PL metric on the marked, this marked surface is a surface with this finite set of points, is a flat cone metric on the surface. So that the cone angle of this metric of the metric D is always inside the set V. So that's our definition. But in reality, we see these polyhedral surfaces are built out of Euclidean triangles. And so if the surface is compact, we can produce the metric, the polyhedral metric, by taking a collection of Euclidean triangles like here and glue them together along their edges by isometry. So this is the picture we can see. So every polyhedral metric on a compact surface is produced in this way. And in doing so, we also produce a triangulations. So by gluing these triangles together, it produces a combinatorics for us. This triangulation may not be naturally associated to the polyhedral surface, so metric. In other words, we are really interested in the isometry class of polyhedral metrics, and this triangulation is sort of some coordinates we used to describe the metric. So knowing this, we can now describe the polyhedral metric by the length function. So So knowing this is a isometric grouping in triangles with this triangulation given, we can describe the metric by assigning every edge a positive number, the length of it. And the only constraint on these lengths are the triangle inequalities. Sum of the two is bigger than the third. And in other words, if I give you a triangulated surface and I assign you every edge a positive number subject to the triangle inequality on every triangular face, then we can produce a polyhedral metric. And there is a curvature. This is also a very straightforward definition. These metrics are flat everywhere except at the vertices. And at the vertex, the curvature is defined to be 2 pi minus the sum of the cone angles at the sum of the angles at the vertex. And so the curvature here is 2 pi minus these angles going into that if the vertex is interior. In case the surface has boundary, then the curvature is a pi minus the sum of the angles. So that's a standard definition. And so here are the positive curvature. This is a positive curvature. This is a convex, and so this is a positive curvature. I guess one don't see it here. So at this center here, this curvature is also positive. So it's concave in, and the curvature here is negative. So by this construction, okay. Now there is a natural constraint, the Gauss-Bonnet, that if the surface is compact, then the sum of the curvature is 2 pi times the Euler characteristic. So this also works for compact surfaces if we use this definition. And now the important notion which we are going to use is a Delaunay. And this is, in fact, is great to work with computer scientists because almost all of their computations based on triangular mesh on these Delaunay triangulations. And so for us, the definition is very simple. I give you a polyhedral metric, and you produce a triangulation built up this polyhedral. And this triangulation is Delaunay if at every edge in your triangulation, you see there will be two angles facing it. So I'm really talking about interior edge. If the edge is in a boundary, there are no constraints. So for every interior edge, there will be two angles facing it. And this triangulation is Delaunay if the sum of the two angles facing every edge is the most pi. Okay, so that's our definition. And this, it turns out, holds the key for the discrete conformal geometry. So let me show you one. Let me show you one picture. This is a real picture. This is a 3D scanned human face, showing that nowadays, especially in the digital world, polyhedral surfaces is really everywhere. And the reality is this is really a triangulated polyhedral surface. There are about 200,000 triangulations in the face, and with around 200,000 triangulations, so we can now make it smooth, and so we don't see it. So we really want to see what happened. We do some sort of discrete conformal change to these polyhedral surfaces. So these are the polyhedral surfaces. Let's go back to the. Sorry. So that's the definition. Let me also emphasize a little bit about the Follanoy and Delaunay triangulations, because it took us a while to figure out why this concept holds a key to define the discrete conformal equivalence. So let me just recall that if I give you a finite set of points, these are the the green dots in the plane, and then it's going to generate a natural cell decomposition of the plane. So this green dots is associated to, this is called the Follanoy cell. The definition is very simple. A point lies in the cell associated to the V if the point has distance, the distance from this point to the site is shorter than the distance from your point to all the rest of the sites. So there is a sort of a biological process. You think of these points as so the growing of some bacteria, and they grow at the same speed, and then it's produce a cell. At the moment that they touch, it will produce, the two cells is going to collide in the common straight lines, and so that will be the Voronoi cell decomposition, and the dual of that is going to be the Delaunay. So Delaunay triangulations here, the purple ones are, the vertices are the given points, and you draw a edge between two vertices if the Voronoi cells share a one-dimensional common edge. And so that's let me just show you that this. I think this is a picture that the biologist convinced that this spot from the giraffe is a Delaunay process. And so the Voronoi process is really quite natural, appeared in biology. Okay. So in general, if we have a 3D scanned data, the triangulation produced in general may not be a Delaunay triangulations. So we need to do some. There are many softwares we would turn that into Delaunays. And so the theorem, in fact, the previous slides already give a proof that every polyhedral metric on a compact surface with a finite set of points admits a Voronoi decomposition, and then you take the dual, you produce a Delaunay triangulation. But there is also straightforward proof for any polyhedral surface. You can turn any triangulated surface with the geometry here into a Delaunay just by keep doing the flips. So if you see one edge where the sum of the two angles is bigger than pi, just flip the edge, and then the sum of the angle is going to be smaller than pi after you flip it, because the sum of the four angles, sum of the four angles is equal to 2 pi. So that's and there is a theorem which says that in a compact surface, if you keep doing that infinite number of steps, every edge will have the sum of the two angles facing it to be less than pi. Okay. So that's this is the definition we propose. I'm going to write it because we're going to use that. So let me write it here. And I will explain, there is really a hyperbolic geometry behind it. But for now, let me define this as follows. Suppose I have two d prime are two polyhedral metrics on a closed surface with a finite set of points marked. Well, we don't know how to define it for a non-compact surface. And we say d and d prime are discrete conformal if we can produce the following finite set of polyhedral surfaces. So if we can find a finite set of PL metrics. So D1 starts from D and then D2 and Dn, and also a sequence of triangulations F1, Fn on the same surface, such that first these triangulations Fi is Delaunay in the Di metric. And two, if two adjacent triangulations are distinct, then the metrics are the same. So the Di metric and Di plus 1 metric are isometric. But we also require that the isometry is homotopic to the identity. So there is this Teichner component appeared, which we have to enforce it. And the third one is the real one, which will make some. So the second process is really the process. We don't change the metric at all, but we do change the triangulation which is basically the flip operation. And the third operation is the essential part. Let me write it. If the two adjacent triangulations are the same, then the metric differ by a so-called vertex scaling. So, okay, let me erase that. So, so you measure. You can find a function u from the vertices. This we're going to think of that as a discrete conformal factor. I can assign every vertex a positive number such that the length function of the di plus 1's metric at an edge with vertices v and v prime is equal to the scaling di v and v prime. Okay, so the process it's probably best illustrated by this picture, which I just erased. So if you look at the boundary of a tetrahedra, we want to do some discrete conformal change of that. First of all, we see a triangulation as I draw. We need to check its Delaunay. Otherwise do some flip operation to make it. And now we are allowed to do the following. You take some vertex and put a positive number here, say k, and I'm allowed to rescale the length of all edges going into v. So it will be something like ka, kb, kc, and the rest is not changing. So this is the process appeared in the third step. This, we call this vertex scaling. And after that, we make sure this is still Delaunay, and at a certain stage, some edge may become so-called critical Delaunay. Some of the two angles facing one edge becomes pi. Then we are allowed to make the second operation, where we change the triangulation. So if the front face we saw here is the quadrilateral is cyclic, some of the two angles is pi, I can remove this edge and put a new edge to it, and then keep going. So this is step 2, and this is the discrete conformal process we like to propose as a candidate. So okay, so that's the same picture. So here is a theorem we prove. Well, before doing that, let me say that this vertex scaling change has some Riemannian geometry background, which will support it. It may be a reasonable definition. So this definition is in some sense the essential component where we actually change the metric, and this has some Riemannian geometry component. It's the following. So suppose I take a Riemannian metric G on a compact surface. I think it's also true on any Riemannian manifold or high dimension. And I give you a positive function. It's a conformal change on the surface. And we now consider a conformal metric, which is G to the U to the 4th power. These two metrics are now conformal. And now we try to compare the distance between 2 points P and Q in the scaled metric and the original metric, the Riemannian distance between the two. And then the estimate is that the difference between the two metric you scaled by the conformal factor at the endpoint is to the third order of the distance. Okay, so that tells you this scaling of the Riemannian distance by the conformal factor at the endpoint is a good approximation to the conformal distance here, and that's in some sense we discretize that, and that's a proposed candidate. So here is a theorem which I'm also right here I like to refer to. I'm not going to prove this today. So the theorem that we proved is that suppose I have a compact surface with a finite set of points, and I give you any polyhedral metric d on the compact surface. Also, I give you any prescribed curvature. So k star is any function on the vertices whose value is less than 2 pi, subject to the Gauss-Bonnet. And then we can produce a new polyhedral metric d star on the same surface, which is unique up to scaling, so that it's discrete conformal to d and the curvature is prescribed. So, so if we go back to the case of a tetrahedra, and we take k star to be k sharp to be the constant. So what this theorem says for this example is that if you give me any tetrahedra, and we can keep going in this process, and in the end we produce a unique tetrahedra, unique up to scaling, where all cone angles are pi. So that's what this theorem says. So in particular, if you take k sharp to be the constant function, which is 2 pi Euler divided by the number of vertices, and then this d star, we call this a discrete uniformization metric associated to d. So this, it turns out, I'm going to tell you, that has some really interesting hyperbolic geometric component, which we didn't know until this year. So here is one special case. For any polyhedral metric on a torus with a finite set of points, then it's a discrete conformal to a unique flat metric on the torus with a finite set of points. So I take k star to be 0. And this theorem, in fact, was proved by Filastri in 2008. I'm going to tell you how to see. I mean, his statement, as you will see, is completely different, but it turns out to be equivalent to what we proved. So that's its process. Okay, so this will you give me any polyhedral torus, and through that process we can turn that into a unique flat torus with a finite set of points. And this, as I mentioned, is really was found before by Filastri. Okay, so maybe I'll say one word how this is proved. I give you any polyhedral metric d like that. You produce a space which I call the discrete conformal class. So DC, you look at the set of all discrete conformal, look at the set of all d prime, which is a polyhedral metric on the surface, discrete conformal to d, modulo isometry homotopic to the identity. So this space, it turns out, is C1 diffeomorphic to a Euclidean space. So this C1 smoothness is the most difficult part of it. So what happened was, we can see, because this discrete process, this space is a finite union of cells. Well, it's a union of cells. Akiyoshi proved, it turns out, is a finite union. And you can make these cells Euclidean polytope, but we need to glue these polytopes together along faces, and that's this second process. And we need to glue in such a way so that the result is a C1 smooth manifold. And it's always difficult. We can make it smooth at codimension 1, but to make a C1 smooth manifold out of polytope gluing at codimension 2 or higher is quite painful. And to prove that, we use the so that this is a C1 smooth, so there's a curvature map where we scale the metric by scaling, map into here where GB is a Gauss-Bonnet. This is a C1 smooth map. Okay, so that's the claim. And to prove this, we really use some heavy machinery. First by Bobenko, Pinkow, and Springborn, which associate any polyhedral metric to a hyperbolic metric. I'm going to tell you a little bit more about it. And then the work of Penner and Riven on cell structures on Teichmann spaces. And so it turns out these cells coming from that corresponds to the natural cell structure on Teichmann spaces. And so the C1 smoothness is really coming from the Teichmann theory. And knowing that, we then proved, so this theorem really says that this curvature map is 1-to-1 onto. And we prove this 1-to-1 onto in 2 steps. The first step is 1-to-1. And by my previous work, I can show this curvature is a gradient of a locally convex function on each cell. And now we also know this curvature is a C1 smooth. And so that implies this function, this curvature is in fact the gradient of a globally convex function. So in other words, the key here is if you have a piecewise convex function on the real line, which is a C1 smooth, and then it's convex. So we just glue these together and produce a C1. So this curvature, by the end of the day, is a gradient of a convex function, and therefore it's 1-to-1. This is like in Jean-Marc's talk this morning. This is a rigidity phenomenon, which, and then we prove it's onto by showing the images is closed. And that's, we analyze how these triangulation degenerates. And it turns out there is this wonderful work by Akiyoshi proved about 15 years ago, which translated into this language will say this space here, which is built out by cells, it has only finite number of cells, and that makes it work. Okay, so that's the basic idea of the proof. But let me show you the second example, which is probably more interesting, is that I give you any polygonal disk D. So this is a simply connected polygonal disk D in the plane. And I take 3 points on the boundary. I call this ABC. So V are the set of vertices. And then I take this polygonal disk and double it, metric double. That will produce a triangulated polyhedral metric on the 2 sphere with 3 points marked. So I'm going to prescribe this curvature K star now. The curvature at the red dot is 4 pi over 3, and the curvature at the rest of the dots are 0. And by the theorem, then we can produce a very special polyhedral metric on the 2 sphere, which is nothing but the metric double of a triangle. So there is a discrete conformal equivalence between the 2 metric, and there is a natural, let me just skip this technical part for now. There is also a natural discrete conformal maps between the 2, sending vertices to vertices. So these 2 are discrete conformal. And now what we are going to do is I give you any Jordan curve in the plane, omega, and you mark 3 points on the Jordan curve. And by Riemann mapping theorem, there is a Riemann mapping from the closed disk to the closed Jordan curve, which is conformal in the interior, and send the 3 vertices ABC to the 3 dots. So there is a unique map. And now what we're going to do is we take a very small number, say 1 over n, and approximate this Jordan domain by the regular hexagonal triangulations. So we can now subdivide the region using, say, 1 over n equilateral triangles, and look at the maximum simply connected domain inside it. And that will be 1-step approximation. So the conjecture is that so as n goes to infinity, this is going to converge to the Riemann mapping from here to here. So this will, if this is true, that will justify that this discrete process is going to converge to the smooth conformality. And that's what this is the main topic today. We proved it today. So I like to tell you this, in fact, is true. So this process can be algorithmic, and so we can now compute the Riemann mapping in this case. Okay. Now, before I will say more about the proof of this. Before I proved it, let me tell you what the first example says. This is Philastri's work, and the discrete uniformization that this theorem tells us, and this is what Philastri proved. So I will convince you in the next few slides, these two are really equivalent. So here is what the philosophy theorem says. I give you any complete finite area hyperbolic metric G on a punctured torus. So this is a torus, and there is this metric. And then he can find a unique lattice, Z plus Z, in the isometry group of the hyperbolic space. When we mod out the hyperbolic space by the lattice, it's really a single cusp. It's in Dave's talk yesterday. This is a cusp, but extend all the way to the conformal infinity. And philosophy says that we can find a unique lattice, unique up to conjugation, and a finite set of points in the conformal infinity. So V primes are here, where the number of V prime is equal to the number of V, such that when we take the convex half these finite set of point V prime in the hyperbolic three-dimensional space, and you look at the boundary of that, it's going to be isometric to your given metric G. Okay, so that's a philosophy theorem, and these two are exactly equivalent. So so let me tell you how to see it. It turns out there is a process we can associate a polyhedral metric, a hyperbolic metric on the punctured surfaces. So here is what we proved. I'm going to tell you how roughly how this is. At least you can see one direction. So one can associate every polyhedral metric D on a surface. The surface is compact here. On a surface with a finite set of points, a cusp hyperbolic metric D star on the punctured surface, so that two polyhedral metric D1, D2 are discrete conformal even and only if the associated hyperbolic metric are isometric by an isometry homotopic to the identity. So this is really in the Teichmann space. I just make it simple by writing D star equals D. Okay, so here is the steps that go into the proof. First, take this polyhedral metric D. We produce a Delaunay triangulation. We know that exists by, say, taking Flournoy cells and then look at the dual. And now you take one Euclidean triangle in the triangulation. Let's call this T. The T has a circumcircle. So there is a unique Euclidean circle B containing this T. And you think of this B as a Klein model of the hyperbolic three-dimensional space and put the hyperbolic metric, which is in a Klein model, and this T becomes a hyperbolic ideal triangle. And this process was really discovered by Bobenko, Pinkow, and Springborn. So let me tell you the magic part here. You associate every Euclidean triangle a ideal hyperbolic triangle. I'm going to call this D star, which has exactly the same underlying set. It's the same, but I put a different metric. The metric is a hyperbolic metric written in the Klein models of the circon disk. So we just take exactly, so start with the Euclidean metric on T, and now I write down the hyperbolic metric in Klein model. Just write down the Riemannian metric on this T, and that will make this T star an ideal hyperbolic triangle. And here is a geometric realization of it, one can see. T star, in fact, is canonically isometric to, so if the Euclidean triangle T is a Euclidean convex half V1, V2, V3, and T star is a hyperbolic convex half of the 3 points. So that's really the picture. You take T in the complex plane, and that's Euclidean, and you look at the ideal hyperbolic triangle with the same set of vertices. This ideal hyperbolic triangle has an induced intrinsic metric from H3, and that is canonically isometric to this. And in this model, here is the amazing fact that if I have two Euclidean triangle S and T, each of that carries the circon disks here, and suppose they have two edges of the same length. We can now glue the two Euclidean triangles by a Euclidean isometry. And this isometry F is also a hyperbolic isometry in this metric. Okay, so this will, in this specific metric, the Euclidean isometry is a hyperbolic isometry, and so we can group these metric using the same Euclidean grouping maps. So it just and in fact you can see it. You can see this picture, and so the proof is quite straightforward. That's a picture. So as I just mentioned, this is canonically isomorphic, and so you have S and T in the complex plane, and you have S star and T star above it, and now the Euclidean motion downstairs is a hyperbolic motion upstairs, and so you stick them together. But the interesting part is that if the triangulation that we started with is a Delaunay, as we begin here, if we take the Delaunay triangulation, this is the Delaunay triangulation, then this surface S star T star is in fact isometric to the boundary of the convex hull. So S and T now can produce a convex hull in hyperbolic space, and this S and T is part of the convex hull, and that's what occurs in the Philostrates case. And so let me go back one more steps. Delaunay triangulation is really closely related to the hyperbolic convex polytopes. This is a well-known fact, but let me just repeat. So suppose I take a finite set of a discrete set in the complex plane, and then we can produce a so-called Delaunay triangulation of the convex hull of the Euclidean convex hull of the finite set. And so this is a picture like that. And so they take finite set of points, you look at the convex hull. Now a triangulation appears in the Delaunay triangulation if and only if the circumcircle of this triangle contains no vertices of V in its interior. So this is the picture that I draw is really part of the Delaunay triangulations. Now if we go to so this is translated into the sum of the two angles is most pi, because this point lies outside of the circumcircle is the same as this algebraic equation. Now if we go to the hyperbolic space, and so I give you this finite set of V, and we take the hyperbolic convex hull V in hyperbolic three-dimensional space. And how do we do that? Well, the hyperbolic convex hull can be defined as the intersection of all hyperbolic half spaces containing V at infinity. But one can look at it the other way, as you take the hyperbolic space and remove all of the half spaces which is disjoint from V. So this ideal hyperbolic polytope is just by taking all half spaces missing V. And now what is this? This B here is a round disk in the Riemann sphere. And that's the same thing as we take a maximum disks in the Riemann sphere missing V. Okay, so you take a maximum disk in the Riemann sphere missing V, and then look at the convex hull of the disk, that's hyperbolic half space, and remove it. And these maximum disks now satisfy exactly the circum disk conditions. And so the circum disks that we produced for the finite set of points are the disks whose interior is missing V. It intersected at 3 points, and therefore the boundary of the convex hull of the circum disks gives you the two-dimensional cells. So for instance, you see this disk here, it's really coming from the circum disk of the 3 points in infinity. So the conclusion is that the T star that Bobenko, Pinkow, Springborn produced is really a part of the face of the boundary of the convex hull. Okay, and now we can actually prove the Philostrates. The Philostrates result is exactly equal to this theorem in the torus case. So what we're going to do is here I give you a hyperbolic metric G on the puncture surface. So what I take is this G is equal to the hyperbolic metric associated to your given polyhedral metric. In other words, every triangle that we see above is replaced by a hyperbolic ideal triangle and glued in the same, exactly the same fashion that the Euclidean isometry used to glue. And now I have a finite set of points in the conformal infinity of the torus that's produced by philosophy. D standard is a standard flat metric in the complex plane and quotient out. So what we're going to do is to take a Delaunay triangulation of V star, of V prime. So we take Delaunay triangulations of that. And now these are equal because, so let me show a little bit fast here. So from D sharp, this is the one produced by discrete conformal. And this D, these two are the same because of the definition and the theorems that I just mentioned. These two are discrete conformal even only if their associated hyperbolic metrics are the same. And the second step is the same as we take G star to be D star. That's how I choose it. And these two are the same is because of the Delaunay construction is a convex hull that I show you. So here we have this Delaunay construction. The Delaunay construction produce a polyhedral metric. When you look at its hyperbolic component, it's exactly the boundary of the convex hull. So these two metrics are now polyhedral metrics with the same associated hyperbolic background metric. And therefore, by the theorem that we proved, these two metrics, the two polyhedral metrics are really the same up to scaling. Okay, so that's and you can go the other way around. It's the same thing. So so now let me sketch the proof of the convergence. So that's a convergence theorem, which I just repeat. So you start with a Jordan curve and take 3 points and then approximate it, and we like to say this is going to converge to the Riemann mapping. The basic idea is it follows from Rodin-Sullivan's solution of Seston's conjecture that Sa mentioned yesterday. So Sa really did a lot of. I just follow the same procedures. And so there are 2 steps involved in Rodin-Sullivan's solution. The first step is you can find a constant L, maybe I should call K, where all these maps are K quasi-conformal. Okay, so there is a uniform K where all of these maps are uniform conformal. That's what Rodin-Sullivan did. And the second is that every limit of convergent subsequence of these guys is one quasi-conformal. And so it has to be a conformal map with this boundary constraints. And so this is a unique guy. So this is a one conformal map with prescribed boundary conditions. And it has to be the Riemann mapping, and therefore everything converged to it. So let me quickly recall Rodin-Sullivan's theorem and Seston's conjecture quickly. That was in Sa's talk yesterday. So let me just mention that, because the proof, our proof of this also produced a new proof of the Rodin-Sullivan's theorems. So I'd like to say, just as a comparison, which is probably easier. So the first is the Kerb-Andreev-Seston theorem, which says that you take any simplicial triangulation of a compact disk, then we can produce a circle packing of the unit disk, whose combinatorics are the same as the given triangulation. Namely, every vertex corresponds to a circle here, 2 vertices, an edge corresponds to a tangent circles, and every boundary vertex corresponds to a circle tangent to the unit circle. Okay, so this picture is unique after Möbius transformation. And now here is, so that's what Sa said. And we also use exactly the same picture. This is a picture from Stephenson. So the Seston's conjecture is, you take a Jordan curve, well, in fact, it's any bounded simply connected domain. We approximate it by regular hexagonal circle packing. And then we produce, by this theorem, produce a circle packing of the disk with the same combinatorics. And in circle packing case, because the triangulations are the same, so there is a piecewise linear homeomorphism sending the centers of the circle to the centers of the circle. And this is what Thurston proposed as a candidate to approach the Riemann mapping. So what Rod and Sullivan proved is that this does converge to the Riemann mapping. And his proof, the first part of his proof that all of these maps are quasi-conformal for some L independent of M is relatively simple. It's a sort of elementary, but it's really a beautiful proof. It boils down to the fact that you look at, so here this triangles are all equilateral. The angle is 60 degrees. And now you look at the triangle here. This is coming from the center, so 3 pairwise tangent triangles. And their first claim is that there is a uniform lower bound on the angles of the triangles appears in this unit disk. And that will imply immediately these FNs are K quasi-conformal. And the reason is relatively simple, that this is because every circle here is tangent to 6 others, and the circles are pairwise disjoint. And from these two conditions, one can see pretty much easily that the ratio of any two radii, which are adjacent radii, is bounded by 100. And now if you have a circle, so this is, let me just say, because the proof is really beautiful. Let me just say quickly. So suppose you have a triangle viewed out of 3 pairwise tangent circles, and the triangle comes from the centers of it. And suppose the ratio of the radii is bounded. Then the angle cannot be too small, because what happened to a triangle with a small angle? You could have a picture like this, with one angle very close to 0 and the other two sum to be pi, or you can have a picture like this. So that's the only possibility for small angles. And now if you look at the circle packing picture, if this occurs, you have 2 small radii and really huge radii. So that will say the ratio of the radii is going to be really huge. And if this occurs, what you see is this picture. And the third circle is really small. And so here you have 2 small circles, 1 large, and here you have 2 large circles, 1 small, and that will violate it. So that's what Rod and Solomon proved. So in our case, the length of the triangle. So in the circle packing case, the length is equal to the sum of the two radii. That's how the circle packing is produced. In the discrete conformal case, the length is equal to the multiplication because it's a scaling change. And we can prove a similar result like these are called ratio lemma. That if you have the same picture here coming from hexagonal triangulations, then the ratio of the conformal factors associated to 2 adjacent triangles is the most 6. But that's not enough to control the angles. Okay, so you can have a triangle whose length is a multiplication. The ratio is bounded, but this does occur. And so for instance, this ratio can achieve 2. This is just half of it. And so it's more subtle. So what we proved so let me move a little bit fast. What we proved actually is the following. I give you a polyhedral disk like that, and we need to do this discrete uniformization process. And the most annoying part is the change of the triangulations here. In step 2, if you change the triangulations, all of the estimate we have before somehow lost. It's very difficult to keep tracking of it. So what we did is the following. I give you a polygonal disk with a regular triangulation. All triangles have the same side. And I need to assume that the 3 boundary vertices are the only 3 one whose angle is 60 degrees, and the rest of it are not 60 degrees. This is to try to avoid flip operation. So if you have a triangle, a boundary vertex of degree 1, when you double it, this will be a triangle whose vertex here is degree 2, and we want to make this vertex flat, and therefore these 2 angles has to be pi. So it's impossible, and that will force us to produce flip operations. And so we assume we don't have that. The only boundary vertices of angle 60 degrees are the given 3, 1, and then what we proved is that I'm going to replace every equilateral triangle by this for n sufficiently large. This is again equilateral triangulations. And after that, for this new triangulation obtained from the previous one by keep doing this, then the discrete uniformization process produced no flips. Okay, so it's just a one-step operation. Just rescale the conformal factors at every vertex, and that will make it into this picture. So they will have the same combinatorics, and furthermore we can control the angles as well. So the angles, by subdividing this enough times, we can control the angles at least, and that will imply the discrete. These approximation maps are K quasi-conformal. So this is a complicated technical part, and so in the end we believe the theorem is still true without this subdivision process, but we don't know how to prove it at the moment. Okay, so the second step is probably more interesting. We want to show that the limit of every convergent subsequence is conformal, and that in the circle packing case, if the limit is not conformal, then this is Rodden-Sullivan's observation that you can produce, because in a finite step, it's going to take a hexagonal triangulation to some hexagonal circle packing to some hexagonal circle packing. If the limit is not conformal, then one can produce a non-regular hexagonal circle packing of the complex plane, where every circle is tangent to 6 others, and then this picture is going to spread out the whole complex plane. And Rodden-Sullivan proves this is impossible. So suppose we have a hexagonal circle packing of some open set. This proves, in fact, a stronger statement. It's not only the complex plane. Any open set in the complex plane, we try to pack it by triangles, by circles, where every circle is tangent to 6 others. And if you have a picture like that, and suppose 2 adjacent triangles have different size, and then you're going to produce self-overlap in some finite stage. Keep extending it. So that's Rodden-Sullivan. And in our case, we have almost the same picture. So if the limit is not conformal, we will produce a Delaunay. This is really through the limit process. Each of the triangulations Delaunay. So we will produce a Delaunay hexagonal triangulation of the complex plane, which is a vertex scaling of the standard one. So this is so the length here comes from the multiplication of the discrete conformal factors from the standard hexagonal triangulation, and we prove that is impossible as well. So so that's a statement in more formal setting. So here V is the vertex. Think of this V as the vertex set of the. So this V here is a regular hexagonal lattice, which is a vertex set of the standard triangulation. The statement is I have a geometric triangulation of some open set in the complex plane, which is Delaunay, and the length of every edge is equal to the multiplication of the two conformal factors coming from the endpoints, and then it has to be a constant, and therefore it has to be regular. And Rodin-Sullivan theorem is in some senses a similar one. Instead of taking the multiplication, you take the sum, and it's going to be a constant. Okay, so that's what they proved. Maybe I think I don't have too much time. So the key step in the proof is a maximum principle. So Thurston proves this maximum principle of circle packing, but I'm running out of time. Let me just skip it. This is really sort of discrete Liouville type theorems. So we also proved a maximum principle in the discrete conformal setting. Okay, so, but as I stated here, it's not enough. And so we need to look at the degenerate case. And so technically, this is more complicated. But let me move ahead. I think I probably don't have too much time. So I'd like to tell you the open question. So by taking some kind of limit process and using the maximum principle, we reprove our Rodin-Sullivan theorem by producing taking a limit and using maximum principle. We will produce a new circle packing whose radius function is log linear. It's a non-constant log linear, and in the discrete conformal setting, the discrete conformal factor, the log of that is a non-constant linear, and then it will contradict in the circle packing case Doyle's theorem that those spiral hexagonal circle packings are self-overlap, and this is what we proved in the discrete conformal setting. There is this hexagonal spiral triangulation which has lots of self-overlap, and that's contradict the assumption that the original circle packings is a circle packing of some open set in the complex plane. But let me finish by telling you the really interesting story, the questions of discrete uniformization for non-compact polyhedral surfaces. So here are some. I did some search. It's really interesting. So there is a work by Thurston which says that I give you any closed set in a Riemann sphere, and you look at the boundary of the convex hull of this X in the hyperbolic space. The induced metric on the boundary is a complete hyperbolic metric, always. Of course, the boundary of the convex hull is a topological surface of genus 0. It's always. So this is the picture in Thurston's note. So look at the boundaries of the convex hull. The ancient one. And then there is a very old work by Alexandrov in 1940s. This is not exactly what he stated. He proved an even more general theorem, which implies this. If I give you a complete hyperbolic surface of genus 0, a complete hyperbolic metric on a surface of genus 0, then it's always isometric to the boundary of the convex hull of some closed set at infinity. So this is sort of the geometry. So the proof of Thurston's theorem, the best, so the modern Epstein modern produced a really fantastic paper, providing details. It's really a great paper. But there are no uniqueness statement you can say. So here is an example. You take omega to be a simply connected domain in the complex plane. Say it's not the complex, it's not the whole complex plane. And let's let X to be the complement of that. It's a closed subset. And then the boundary of the convex hull is always isometric to the hyperbolic plane. So we think of X to be the complement here. So the omega is a dome, so there is the boundary of the convex hull is sort of the dome over. Omega is the region underneath it. X is this complement here. These are the X's. So according to Thurston's theorem, this is isometric to H2. And so here is really the picture. If you look focused on the complex plane, there is no hyperbolic geometry. It's just the Riemann surface. This is the Riemann mapping. We'll say there is a conformal map from the boundary to the boundary. And you look at the convex hull. Well, Thurston theorem says that if you look at the boundary of the convex hull, and that's isometric to the hemisphere, which is the hyperbolic pieces. And we also see the geodesic laminations are coming from these here. So that's the picture. Now here is what I would propose to understand the non-simply connected polyhedral surfaces. So here is a picture. I have a polyhedral surface which is non-compact, simply connected, and we have these triangulations here. And according to the classical uniformization, it should be discrete conformal, which we don't know how to define, to the complex plane with a discrete set, and this standard is a standard Euclidean metric, or the open disk with a discrete set, and this standard is again the standard Euclidean metric. But this process, the above process, is really a finite process. It doesn't work well for infinite triangulations. And so the way to go is just go to the hyperbolic space, and from here I will produce on a punctured plane, a plane with a discrete set removed, and put a Poincare metric here. Or there is a open disk with a discrete set removed, and put a Poincare metric here. And this side, according to the Delaunay construction, should be the boundary of the convex hull of some discrete set in the complex plane or the disk. So the discrete uniformization should somehow says that you give me any complete hyperbolic metric, it should be isometric to the boundary of this discrete set, boundary of the convex hull discrete set in a plane. And that's what I like to propose. Oops, I probably should stop. Okay, let me tell you this. Let's call a closed set in the complex plane. X is of circle type if every connected component of it either points or around disks. So the conjecture is that I give you any complete hyperbolic surface of genus 0. It's going to be isometric to the convex hull of boundary of the convex hull of a circle type closed set. And the circle type closed set is unique up to Möbius transformation. This is a very strong assumption. I don't know. But it's highly possible that uniqueness should be true when X contains no Cantor set. So X has a countably many connected components. It should be true. And so the discrete uniformizations here. So let me tell you, there are a couple evidence for that. And Igor Rivin, which proved this theorem, which was theorem C in Jean-Marc's talk. It was over there. That's exactly the statement. And Jean-Marc himself proves that if X is a finite union of round closed disks, and this conjecture is true. But at the moment, if you mix these two, it's a finite set of points and finite set of disks, it's open. But the point is that if you have some disks here, the boundary of the convex hull is no longer polytopes. It's more strange phenomenon. Okay, so since I'm running out of time, let me just say I'll stop here. Thank you very much.